Trev, what were you doing?
I'm learning about diffusion.
There's a fair amount of information in here, there's a fair amount of information here. That's not a good concentration gradient, Trev.
Terrible.
So part 2 of the video, we're still on topic 2.2 of our biology. It's all about diffusion and the effects on CF, so we're now actually linking stuff to cystic fibrosis.
Well, as promised, on to diffusion.
Yep.
So last part 1 we did mention diffusion, we did define it, but we'll do it again just in case you'd forgotten. Diffusion is the net movement of stuff, particles, from high concentration to low concentration until equilibria is reached. That means it's equal on both sides. It's net movement because it's a continuous process and it changes a bit. And it's passive, it uses no energy.
Yep, so I'm just putting the marking points on the board there.
Alright.
So, when he says particles, it's small particles. We'll get onto the bigger stuff in a minute. So how that works in reference to what we did in the last part, which is the phospholipid bilayer.
Yeah.
So if I draw
It works in the actual membrane. Remember we had the, it's a bilayer, so there's 2. So we have our 2 tails going inwards because they hate water, hydrophobic.
Yep. So small things you can sort of picture can fit in here.
Yeah.
They can
Stuff like carbon dioxide, oxygen, stuff for the gas exchange, they fit through. Bigger stuff doesn't, and we'll get into that in a second.
But first, there's another, it's just like diffusion, but
is.
for water you should be familiar
It
with
is.
from GCSE.
Both of these GCSE. It's called osmosis. Osmosis is the diffusion of free water particles from a high concentration to a low concentration, but this time it's through a partially permeable membrane, so that's pretty handy. Again, it's passive and it keeps going until equilibrium is reached. Think about free water molecules, water molecules that aren't attached to things. Like if you had put sugar in water, they'd attach, and these ones wouldn't fit over the partially permeable membrane because they're too big. Sorry, I got my tongue tied there.
So I'm not going to draw it again, but the exact same thing for osmosis. So we just mentioned stuff that's bigger that cannot fit through this area. There's a special name for that. It's on this side, it's on the diffusion. It's facilitated diffusion.
It is. Stuff that's too big needs some sort of way to get across. So we use carrier proteins. And we mentioned before, we have this in our membrane, phospholipid bilayer thing. We had the phospholipids line up, and in the middle we had a channel protein. And this is what we use as a facility, or facilitator, that's why it's called that.
I'll draw another one just to represent. So if this has sort of this distance here, you'd have something like this.
Yeah.
And that would have to go through here.
And it would be carried. Because this one's diffusion as well, it still doesn't use any energy, but it's just for bigger things. It uses a carrier protein. I don't think you need to know what it is.
Not in this one, no.
And again from high concentration to low.
Yep, so all the same points would just be here, so I'm not going to write them all out again. But there is one just like it that's completely opposite.
Yeah, this one's called active transport. Difference to this one is it moves against a concentration gradient. It goes from low to high, still uses carrier proteins. You have to know what this one's called. It's called ATP, which is active transport protein, so it's not that hard to remember.
It requires energy.
Yeah, and it requires energy. Because it's against the concentration gradient, it needs something to keep it going. This one requires energy, and it's the same sort of thing.
Except the arrow would be going that way.
Yeah.
So we're not going to draw it again, just know it's reverse. Yeah, there's 2 more types.
There is.
It's called exo and endocytosis, so let's swap
sides, yeah.
I'll do it in red.
Now these ones are for stuff that's even bigger, like a big bulk movement of stuff. Now this is stuff that won't fit in the channel. So we use vesicles. You should remember, well, you should know, that these are sort of membrane-bound sacs, and they get filled with stuff. I'm going to show the diagrams in the book now. And in exocytosis, which is like exit, these sacs get filled and they move up to the surface where it splits, and stuff flies out, and then it bounds to the top. Endocytosis, which is like entrance, is the opposite. That's pretty much the gist. And they use vesicles, and yeah, bulk movement of lots of things.
Yep. So, obviously you've done the course before, so it's just revision. We're not going to go into any more detail than we just have done, but now let's actually apply this to cystic fibrosis.
And how the membrane's affected. Alright, let's crack on.
Alright, we're back.
We are. Hello.
To finally answer the question that Trev asked me in part 1 of this video.
Yeah. Big question. Why is CF mucus so sticky?
Yes, so first we should know that it's to do with the lungs, the respiratory system.
That's where most of the mucus in the body is. Not all of it, we'll get into that later.
And it makes sense to look at a healthy person first, I think.
It does.
For the cilia to move it, you need ideal conditions, essentially, of the mucus.
So the mucus can't be too watery and it can't be too sticky.
If it is too watery, water's removed so that it's not too watery.
Water's pumped away from the mucus, through the membrane, into the tissue fluid.
And the opposite, if it's too sticky, it's pushed in.
Yeah, and you want to get rid of the mucus. Oh, why do you want to get rid of the mucus?
Well, because mucus can trap harmful microorganisms called pathogens, which can cause illnesses. And essentially, with CF, you can't regulate these conditions.
Yeah, basically what happens is you can't get rid of the pathogens, and that's why they get so ill.
But enough of this basically malarkey, let's get on to it.
Yeah, let's get onto it properly. So, we're going to start with someone who's healthy, and let's have excess water.
Yeah, that makes sense.
Alright, so at the top we have, this is the area of the mucus, your lungs. You might have to label this. So this is the apical membrane, that's the basal membrane.
And here's your tissue fluid.
It is. Okay. Alright. So, excess water. So you want the water to go that way.
Yes. It says excess water. That doesn't mean all the water's up here.
No, there's still
some
water's
water's
here,
here,
some water here.
But a lot, too much here.
Too much is here, yeah.
So what you want to do is you want to get rid of that water, as Triv said. So to do that, what first happens is the sodium is actively pumped. This is active transport.
It's pumped
through the
down.
sodium channel.
Yeah, through the channels we talked about before.
Like this.
And that's moved down here. Now, because the sodium is positive and chlorine is negative, all of these ions are pretty much everywhere, by the way, as well.
Yes.
But it basically pulls down the chlorine as well.
Yes, it creates an electrical gradient, is what it's called.
And that pulls the chlorine down. Now, when these two come together, they make a lovely thing called sodium chloride. Should recognise that as salt.
Because this is now salty.
Yeah, less of the water is free, so the movement of free water particles goes down.
And that's done by osmosis, as you should know. It's a GCSE concept, but also developing a bit with the phospholipid bilayer. Yeah. It can go through those small gaps we did just a minute ago.
Yeah, so water just comes straight down.
Essentially, just don't put it through one of these channels.
Yeah. It doesn't need a channel, it just needs to go for the gaps. And water comes down, that makes it less sticky.
And because it's osmosis, it's until it reaches equilibrium. When it's equilibrium, this will not be too sticky. It will be perfect for the cilia to remove.
And this may keep happening because mucus will keep moving and water will keep moving. Yeah, that goes on.
The opposite of that is if you have too little water up here. So
so let's annotate that again. Cross all this off. So you've got too little water that side. You want to put water that way. And this is where we start using our CFTR channel.
Yes.
Which is the thing that doesn't work or isn't even there in CF. We'll get to that in a minute. So this is our CFTR channel. You might have guessed, there's only two things that are moving across iron-wise. It's going to be chlorine.
Yes.
So too little water here. So chlorine is actively pumped from the bottom to the top, chloride ions. Now, like before, this creates an what's it called?
Electrical gradient.
Electrical gradient. There you go.
So sodium does what chlorine did before.
Yeah, it gets pulled across because of the opposite charges, and they come together and make a beautiful thing called salt, and this pulls water up. Because less of the water here is free, so there's a bigger concentration gradient, so they move up.
Now, Triv briefly mentioned there, person with cystic fibrosis does not have this, or if it does, it's non-functioning.
Yeah, it doesn't work, which is bad.
That's very bad. The reason it's bad is because sodium, this channel, will be constantly open, pumping sodium down this way.
Yeah, because you can't put any chlorine up this way, no sodium will want to go this way, so no salt will go this way, so basically no water ends up going to the top. So it becomes so sticky that the cilia can't move it, have to stay down there for ages, and well, the only way to get rid of mucus other than that is coughing, and that's bad. That does really bad things to your alveoli.
So Na goes down, Cl's forced to go down because this goes down. Cl then cannot get up there.
No. And this,
closed. As
I learned before, this is pretty much what happens when you have too much water. So water just constantly pulls down, making it even worse.
And that's what gives us sticky mucus.
It is, and that's the answer to the question.
Yeah, so we've finally done that. We also briefly mentioned at the beginning of this clip, mucus isn't just in the respiratory system. So the next video is topic 2.3, and we go on to that.
Alright.
Now I think we can sum up part 1 and part 2.
I think we can.
Let's do it.
Alright, let's crack on.
Yeah. Alright.
Summary time.
We've still got part 1 and part 2's video.
We are, both at once. So, what did we do?
Well, it's topic 2.2, and we started off with proteins and amino acids, making them up.
Yeah, we looked at amino acid and the basic structure. Carboxylic acid end at the amine end.
and the R group being the thing that can change its chemical reactions, change what it is.
That will change the shape of the final protein when they become a chain.
So just a straight chain is a primary structure.
Yeah.
Secondary structure, you have an alpha helix and a beta plated sheets.
Yeah, then there's tertiary structure, we start adding these things together, and quaternary where you add more of those sort of line.
And the different bonds that are in there. We're not going to go through them all again.
No,
because
it's
that's the point of the video.
Yeah.
We went on to phospholipids.
We did, and what a phospholipid is, lipid with a phosphate bit on it.
Yeah, and then the phospholipid bilayer, because that's the most sturdy construction based on the fact that the hydrophobic tail and the hydrophilic head.
Yeah.
That's the best way for it to go. That led us into diffusion
It did.
related to that.
Yeah, all the types of diffusion as well.
Yep. So first is just diffusion as you know it at GCSE,
Yep,
and that can go
osmosis.
through. Yeah, they can both go through the phospholipid bilayer.
Then facilitated and active transport. They use carrier proteins, one goes one way and goes the other way.
Yep. Active requires energy.
The other one doesn't.
Then there's endo and exocytosis, which is big bulk
Yeah.
vesicles stuff.
Movement of things. And then they went on to regulating of water in mucus.
And that answered the question of why is mucus so sticky? The idea that water is constantly removed if you have CF because of the CFTR protein not being there.
Yeah, the channel's
or
not working.
functioning.
Yeah. That's pretty much suggested what we did.
Yep, that's topic 2.2 summed up in a nutshell.
Yeah.
We'll see what topic 2.3.
Alright, let's do it.
Wayne Lack and James Trevette.
Let's crack on.